Hi guys, in this video we'll take a look at Introduction to Geometric Series, the result of the simplest geometric series formulae, examples, and then we'll finish with a summary.
So what exactly is a geometric series? We know that we can generate a geometric sequence by multiplying a common ratio repeatedly to the first term. Let's say we have the geometric sequence 2, 6, 18, 54, and so on. At each stage we are multiplying by a common ratio, which in this case is 3. So the first term, which we denote as A, is equal to 2, and the common ratio, which we denote as R, is equal to 3. Instead of considering the sequence, we can add the terms. Again, we have this sequence, which is in this case 2, 6, 18, 54. Or instead, we can generate a sum by adding these subsequent terms, 2 plus 6 plus 18 plus 54. When we sum the terms of a geometric sequence, the result is called a geometric series. In general, we start with a first term A, and then we add the next term, which will be AR, where again R is the common ratio, and the next term will be AR squared, and so on, all the way up to the nth term, which is AR to the power of n minus 1. This, in general, is called a geometric series. Now, we can calculate the value of a certain geometric series by continually adding terms. So to work out our 2 plus our 6 plus the 18 and then plus the 54, we can just start by adding 2 plus 6, and this gives us 8. And then 8 plus 18 is 26. And then 26 plus 54 is 80. However, if we wish to calculate all of the terms up to the 10th term, this will be a long process, and even longer if we wanted to say all the terms added up to the 100th term, or the 1000th term, and so on. Again, in this case the sum would be 2 plus 6 plus 18 plus 54, and then we would have the 100th term after all of the terms in between as 39,366. We'd like to be able to calculate this series directly with a formula. Let's take a look at the result of the simplest geometric series. Before we can find the formula for a geometric series, we need to develop a particular result. We'd like to consider the sum 1 plus r squared all the way up to r to the power of n. In order to find a formula for this, we can multiply by a special factor. So we take our 1 plus r and r squared all the way up to r to the power of n, and then we multiply by this special factor 1 minus r. At the end, we will divide by this to get our result. When we expand this out, we obtain a simple result. So let's have a go at expanding this out. The 1 times the 1 gives us a 1. The 1 times the minus r gives us a minus r. And then we have the r times by the 1, this gives us a plus r. And then we have the r times by the minus r, this gives us a minus r squared. But the thing to start noticing is that some of the terms are starting to cancel out. Namely, so far, the minus r and the plus r. This cancels out to give us 0. If we continue, we have the r squared multiplied by the 1, which gives us plus r squared. So again, we see that this has cancelled out. And then our next term with the r squared with the minus r will give us a minus r cubed. But by continuing on and looking at the end of this, so we have a plus ... If we consider our term just before the last term, so r to the power of n minus 1, the second to last term, being multiplied by the 1 and the minus r, well, r to the power of n minus 1 times 1 will give us just plus r to the power of n minus 1. And then we have the r to the power of n minus 1 in here, multiplied by the minus r, which gives us a minus r to the power of n. And then we have the r to the power of n multiplied by 1, which is a plus r to the power of n. And then finally, the last term is the r to the power of n multiplied by the minus r, which is minus r to the power of n plus 1. But again, we have this cancellation here, and due to this cancellation, it's going to happen all the way through. And so the only terms we actually keep after doing this expansion are the first and the last terms, so the 1 and the minus r to the power of n plus 1. Then, by dividing, we obtain a result for our initial expression. We're just looking for the formula for 1 plus r squared, all the way up to r to the power of n. And then, by dividing, this is going to be our result that we got just before, which is the 1 minus the r to the power of n plus 1. And then we divide by the factor we multiplied by in the first place. If we have a little look, that is the 1 minus r. We introduce this to get this simple result, and so now we divide by it, and we have the 1 minus r on the denominator. Now, out of interest, this result only holds when r is not equal to 1. This is because we divided by 1 minus r, and so clearly that would be dividing by 0, which doesn't allow the result to hold. So just to clarify, this result holds in all situations where r is not equal to 1. So let's consider a particular case. We will consider the case when r is equal to 2, so hence that's okay, it's not 1, and then the case that n is equal to 5. The left-hand side of this formula is going to be the powers of 2 from 0 to 5. So 2 to the power of 0 is 1, and then we have the 2, and then we have the 2 squared, and then we have the 2 cubed, and we're going all the way up to 2 to the power of 5. Now, this formula says that this is equal to, let's have a look at our formula, 1 minus 2 to the power of 6, that's our n plus 1, and then we divide by 1 minus r, which is 1 minus 2. And then looking at the denominator, 1 minus 2 is minus 1, and so dividing by it just flips the numerator. So we get a 2 to the power of 6 minus 1, and by working out 2 to the power of 6, that's 64. 64 minus 1 is 63. Again, just to clarify about this minus 1, dividing by 1 is the same as doing nothing to the original expression, but the minus gives us a turning around effect by expanding it out and distributing the minus to both terms. You get a minus 1 and a plus 2 to the power of 6. So how can we determine the geometric series formulae? For a general geometric series, we use notation for the sum to n terms. We write s subscript n is equal to the sum of the terms. We write them as u1 plus u2 all the way up to the nth term un. With our earlier result, we are now ready to evaluate a general geometric series. In general, our sum is s subscript n, and we have our first term a, and then our second term will be the AR with the common ratio R, and then we have our AR squared, all the way up to our nth term. Now be careful, this is the AR to the power of n minus 1, that's our nth term. To begin, we can factor out the common a. The word common here isn't referring to the common ratio, but the fact that a is common to every term. We can factor out the a, so we have the Sn is equal to the a, and then we factor out the a from all of them, so we just have a 1, and then we have a plus r and a plus r squared, and this goes all the way up to our final term, which is r to the power of n minus 1. Now we can use our earlier formula to determine the expression in the bracket. We have the expression 1 plus r squared, all the way up to, this time, r to the power of n minus 1. And so by adapting our formula, we get that this is equal to 1 minus r to the power of n this time. In the previous formula it was n plus 1, but now we're ending at n minus 1, so the last term is n, and then again we divide by the 1 minus r. But to be clear, this only holds in the case that r is not equal to 1. Now sometimes we write this expression differently, by multiplying by minus 1 to both the numerator and the denominator. We have that our expression 1 minus r to the power of n divided by 1 minus r, if we multiply both to top and bottom with a minus 1, it just flips around both the top and the bottom, and so we get an r to the n minus 1 on the top and an r minus 1 on the denominator. Now, which expression we use in which context depends on the value of r. If r is bigger than 1, then it helps to use the second expression, because you'll have that r to the power of n is bigger than 1, i.e., let's say r is 2, then 2 to the power of n in general will be bigger than 1, or it will be equal to 1 in the case that you have n equals 0. If you have r being strictly less than 1, say 1/2, then you'll have, say, half to the power of n, and that'll be less than 1, and so it's helpful to have everything positive, and so we have it as the left expression. Again, it doesn't really matter, it will all work out in the end, but as we saw before, we had to multiply by the minus 1s on top and bottom and flip it around to get the 2 to the power of 6 minus 1, but if we had it in this form to start with, it would have been slightly easier to see. Then we can bring back the factor of a. This gives us our final expression. The sum to n terms is just a multiplied by this, because all we did was to simplify this expression, and so we bring back the a and we have the, let's say, the a on the numerator with the r to the power of n minus 1, and again we divide by r minus 1. Just to be clear, still, this formula only holds in the case that r does not equal to 1. Out of interest, if r equals 1, let's have a look at our series. This is the expression for our series, and if r equals 1, then all of these terms actually go away, as in the r terms. So we're just left with a plus a plus a plus a. And this is really an arithmetic series, not a geometric series. So it makes sense why this formula shouldn't hold in this case. We should really treat it as an arithmetic series. We can use this formula to directly evaluate a geometric series. As earlier, let's say we have the sum 2 plus 6 plus 18 plus 54 all the way up to the 100th term, which is the 39,366. Now, this would be rather difficult to calculate directly. It would take a long time to add all of these terms up, but we can use all the critical values and our formula to calculate its value. We can see that the first term is 2, and we can recall that the common ratio is 3. To get from 2 to 6, we've multiplied by 3. And we can recall that this term is such that this is the 10th term, so n equals 10. Therefore, by evaluating the sum up to 10 terms, we have the first term, which is a, that's outside, so that's 2. And then we multiply by the r to the n minus 1. R is 3, so that's 3 to the power of 10, and then we minus the 1. That's all multiplied by the 2. And then we divide by the r minus 1, so that would be 3 minus 1. If we calculate the value of 3 to the power of 10, we get 59,049, and so by minusing 1, we have on our numerator 2 multiplied by 59,048, and then the denominator is also 2, and therefore by cancelling, we get that the value of the sum up to 10 terms is going to be 59,048. Let's take a look at some examples. Our first example says that given a geometric sequence with first term 5 and common ratio 2, we're asked to find the sum of the first 15 terms. Our first step is to recall the geometric series formulae. We have that s subscript n is equal to a multiplied by r to the power of n minus 1, and then we divide by the r minus 1. Our second step is to substitute in the values in the question. We're looking for the sum of the first 15 terms, and so we're looking for s subscript 15, and we use our first term in our common ratio, that's 5, and then we're doing the r to the power of n minus 1. Well, r is 2, and so we have the 2 to the power of 15, that's our n, and then we minus 1, and then we're dividing by the r minus 1. Well, r is 2, and so we have 2 minus 1. Our third step is to simplify the calculation. We have that s subscript 15 is equal to the 5, that's the first term, multiplied by 2 to the power of 15 minus 1, because 2 minus 1, the denominator, is precisely 1. And then the 2 to the power of 15 is 32,768, and so we minus the 1 and we get 32,767. And for our last step, we write down the answer, and we have that S subscript 15 is equal to 163,835. Our second example tells us that given the second term of a geometric series which has r strictly greater than 0 is 4.5, and the fourth term is 10.125, we're asked to find the sum of the first 30 terms to the nearest whole number. Our first step is to recall the formula for the nth term of a geometric sequence. The nth term of a geometric sequence u sub n is equal to a multiplied by r to the power of n minus 1. Our second step is to recall the geometric series formula. We have that the sum up to n terms is equal to a, the first term, multiplied by r to the power of n minus 1, and then we divide by the r minus 1. Our third step is to form an equation using the second term. We've been told that the second term is 4.5, and therefore using our nth term formula, we have that AR, because n is 2, so we have AR to the power of 2 minus 1, which is AR. We have that AR is equal to 4.5. Our fourth step is to form an equation using the fourth term. Again, by symmetry, we have AR cubed, again because 3 is 4 minus 1, is equal to the value in the question, which is 10.125. Our fifth step is to solve the equations. Putting the second equation first, we have the AR cubed is equal to 10.125, and then our first equation, which we're now going to have as our second equation, is AR is equal to 4.5, and again, I've done this in this order because I'm going to be dividing, and by dividing, I get just r squared, because a cancels with the a, and I have 2.25 on the right hand side by dividing. By square rooting, we have that r is equal to 1.5. Now, you may be thinking it's plus or minus 1.5, but in the question, we were told that the r is strictly greater than 0. And therefore, to find the value of a, we use the second equation, ar equals 1.5. We have a multiplied by the value of r, which is 1.5, is equal to 4.5, and this gives us our value of a as being 3. Our sixth step is to substitute in the values that we have found. We are looking for the sum up to 30 terms. And therefore, by using the geometric series formulae, we have the a r to the power of n minus 1 divided by r minus 1. So that is the 3 multiplied by the 1.5 to the power of 30 minus 1 divided by the 1.5 minus 1. Our seventh step is to simplify the calculation. We have that s subscript 30 is equal to, let's have a look, 1.5 minus 1 is 0.5, i.e. 1/2. And when we divide by 1/2, it's the same as having 2 on our numerator. And therefore we have the 6 by combining it with the 3, and we multiply by the 1.5 to the power of 30 minus 1, and this gives us 191,750.0. Now we have our 0.0 because we're looking for, as in the question, our sum to the nearest whole number, and therefore we need to be careful, since when we multiply by the 6, we may end up introducing an extra whole number, but in this case we won't because it's 0.0. Let's say it was 0.1 at the end of this 191,750. This would give us a 6 multiplied by 0.1, which is 0.6, and when we round, that would give us a 191,751. So it's important to keep enough accuracy early on in order to be able to find the overall final answer correctly. Our eighth step is to write down the answer, and therefore by multiplying, we have that s subscript 30, the sum up to 30 terms, is equal to 1,150,500. Our last example tells us that given a geometric sequence with first term 13 and common difference -2, we are asked to find the sum of the terms between the 6th and 12th terms inclusive. Our first step is to recall the geometric series formula. We have that S subscript n, the sum up to n terms, but specifically starting from the first term, is equal to A multiplied by the r to the power of n minus 1, and then we divide by the r minus 1. Our second step is to express the sum as the subtraction of two sums. We are looking for the sum between the 6th and 12th terms inclusive. And therefore, if we calculate the value of the sum up to 12 terms from the first term, we overcount by the first term, the second term, the third term, the fourth term, and the fifth term. We want the sixth term. And therefore, we subtract S subscript 5, because that contains precisely the first, second, third, fourth, and fifth term. Our third step is to calculate the sum up to the 12th term. We have that S subscript 12, this is the sum up to 12 terms, is equal to, using our geometric series formulae and the values given in the question, the first term is 13, and the common ratio is -2, so we have our 13 multiplied by -2 to the power of 12, and then we minus the 1, and finally divide by the r minus 1, which is -2 minus 1. This gives us 13 still, and the -2 to the power of 12 minus 1 gives us 4095. And then the denominator becomes -3, that's the -2 minus 1. And so by multiplying and dividing, we end up with precisely -17,745. Our fourth step is to calculate the sum up to the fifth term. If we look at S subscript 5, that gives us the first term up to the fifth term all summed together. And again, this is the first term 13, and then we have the common ratio -2, but this time to the power of 5, and we minus the 1, and we divide by the r minus 1, which is the -2 and then -1. This gives us 13, and then we have the -2 to the power of 5, which is -32, and then we minus a further 1, which gives us a -33. And then we divide by the -2 minus 1, which is again -3. And this gives us 143 for the sum up to the fifth term. Our fifth step is to subtract the two sums. Again, we were considering the sum up to the 12th term, and then we were minusing the sum up to the 5th term, and by plugging in their values, the S sub 12 was -17,745, and then we're minusing a further 143, and this gives us the value of the sum from the 6th term up to the 12th term as precisely -17,888.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face, and together, let's make A-level maths a walk in the park.